Ben mesela şey
So far we were concerned with the as a user, how do I use the file systems as an operating system user? I am concerned with how the files are named. Okay, what kind of operations I am allowed to use on the files, like the creation and deletion and the opening and writing, etc. And what directory tree looks like, and similar interface issues. These are from the user point of view of the files from the operating system area. How about the implementation issues? As an implementer of the operating system file systems, okay, I am interested in how the files and directories are stored. How do I keep that information on the disk? And how the disk space is managed? And how to make everything work efficiently and reliably. These are my concerns as an operating system implementer. So when I say file system implementation, we will look at these kind of issues now. Okay, so the physical disk, okay, we will talk mostly about this later when we talk about the devices. We might talk about a little bit about the flash disks, flash drives, okay. But we will talk about mostly about disk. The disks are they have sectors. They are structured like this. Okay, this is my disk. Inside my disk, I have concentric tracks. Okay, and the outermost track is the important one because it has this. It has these sectors, and each one has a fixed number of sectors. And one of these sectors is called sector 0. Okay. And this is sector 0 of the disk is called master boot record, and it is used to boot the computer. Okay, is the structure of that master boot record? I will not give. We will not go into details of that master boot record. But if I wanted to look at the entire structure of the disk, it is structured like this. At the beginning, this is a logical structure, of course. The physical structure is like this. Okay, this is my physical structure. This is my sector 0. But my logical structure is this. At the beginning, I have master boot record. Then I have my partition table, and these are my partitions. What is this partition? This partition is some part of the disk itself. Each disk partition might have its own file system. Okay, the file system here might be NTFS. Okay, Microsoft file system. Here it could be ext3 Linux file system. Here it could be FAT32 file system. It might be different for different disk partitions. Okay, so this is the general structure of a whole disk. All this by what I mean by all this, by this physical disk. So let's look at this sector 0 now. This part. Okay, the sector 0 is a master boot record, and it is used to boot to computer. When the computer is booted up first, when you turn on your computer, you read this record, sector 0 MBR, and that's that it contains special code. Okay, we will come to this MBR later. Okay, at the end of the MBR, I have this partition table. Partition table is this part. It says that, okay, I have 3 partitions in this disk. The first partition contains NTFS. The second partition contains the ext3. The third partition contains a FAT32 partition file systems. And each partition starts from this address and it ends it here. So this one gives all the information about the partitions on that disk. Okay. This table gives the starting and ending addresses of each partition. How many you have, it depends on your system. Okay? And one of the partitions in the table is marked as active. Okay, one of the partitions is an active partition. Okay, let's say, says that, okay, this partition table says that, this partition is an active partition. That means the second one, this one is my active partition. Okay, this is my active partition. What's an active partition? When the computer is booted, the BIOS reads in and executes the MBR. Okay, the MBR, remember, is the sector 0 of the disk. The BIOS is the program code that resides in read-only memory inside the computer, inside the ROM. When you boot up your computer, first BIOS reads this MBR, and that MBR is part of the operating system. It boots your computer, it starts your computer, it initializes your operating system. Okay? The first thing the MBR program does is locate the active partition and read its first block, which is called the boot block, and execute it. So this MBR, the task of the MBR is to look at this partition table, find the active partition, and read the special part of the active partition, which is called boot block. Okay, it reads that boot block, and boot block is the actual operating system code, and it executes it. When the boot block starts executing, your operating system starts executing. Okay, so if you have more than one operating system installed on your computer, for example, one in this one, one in this one, and one in this one, you can have different boot blocks for each of them, and depending on your MBR code, you may select, instead of selecting the active partition, you might select different partitions, and you might boot up your computer with a different operating system. Okay, so this is a multiple boot operating system. If you like, you can run Linux or Windows or some other operating system on your computer. You have this kind of a structure. If you don't make any changes, your active partition will be selected, and the boot record of that partition will be executed, so your computer will boot into that operating system. Okay, so this is what happens. This is what happens when you boot up your computer. You read your MBR first. Okay, from the MBR, it inspects the partition table. It finds the active partition. From that active partition, it reads this boot block, and it executes it. Okay, it executes it. There are some special MBRs. Those special MBRs will ask you which file system you want to boot from. You can choose the one that you want to boot from, and then you can have multiple boot file system or operating system in your hand. Okay, so let's look at the details of these partitions. Okay, inside these partitions we have the boot block and the super block, and we have our, depending on our file system, you might have information about the inodes, root directory, files and directories, and some special spaces. So since we are dealing with the file system implementation, we need to know the details about the entire disk first and the disk partitions later. Okay, any questions? Okay, then let's move on. The super block after the boot block, remember this boot block is the part of the operating system. That's the whole operating system. It initializes all of your processes and everything. Okay, the super block contains all the key parameters about the file system. Okay, you might need different information for different file types, with different file systems, NTFS or ext3, etc. You read all those parameters in, and you do your first housekeeping operations on using those parameters, and super block has that information. So these two blocks are very, very important. If something happens these two, then you have your disk partition crash or the operating system crash. or more seriously, if something happens to your MBR, okay, if something happens to your MBR, then most of the time you lose all of your information in your disk. That's why very special permissions you need to have in order to access this MBR or the boot block or the super block. Otherwise, those bad code, intentional or unintentional, might modify these parts of the disk, which will cause you lots of problems later. So this is the super block. Okay. So let's look at this file and directory structure inside each disk partition. How do I keep my files on the disk, and how do I keep them organized? Do that kind of stuff. Okay. Implementing the files. The first one, the very simple one, how do I implement the files, is the contiguous layout. In the contiguous layout, this is the picture. Let's say I have 1, 2, 3, 4, 5, 6, 7 files in my file system. Okay. And file A needs 4 blocks, file B needs 3 blocks, file C needs 6 blocks, etc. If I put my files one after the other, like this one, this might be the picture. Okay. Contiguous allocation, contiguous layout is very simple. Okay. When you create your file, okay, if the file needs 4 blocks, then I put it in here. Then file B needs 3 blocks, and one after the other. It is very easy, no space allocation problem. And when I start reading my file, I sequentially read all of my bytes, all of my blocks, one after the other, no problem. The problem here is that, what is the problem with this approach? If I do my file allocation this way, contiguous allocation, there might be problems regarding what? There might be fragmentation problems. Why? Because if I delete my file B and if I delete my file F, so 5 free blocks here, 6 free blocks there. If I need a space for 10 blocks, even though I have 11 blocks free, I cannot make it happen. I cannot make free space for the new file, which will take 10 blocks of space. So I need to move this file A, E to the beginning, which is lots of time, which is lots of problem. We had this similar problem with the memory virtualization, right? With the virtual memory. Remember we said that if I stack my programs on top of each other, if I need space for a new process, I might have some fragmentation problems. I need to move my code from one part of the memory to another part of the memory. Those are very bad problems. I mean, not bad really, but it will take some CPU time. And again, I will have the same problem here. This fragmentation is a serious problem. What is the other problem for this kind of contiguous layout file implementation technique? Fragmentation is one problem. Second problem, maybe more importantly,
İstediğimiz kesime ulaşamayız direkt.
Allocation
İstediğimiz kısmı direkt olarak okuyamayız.
o daha kolay esasında. İstediğin kısmını çat diye okuyor. Çünkü diyorsun ki file buradan başladı ya. E dosyasının 5. bloğu çat diye buraya geliyorsun. Yani E'nin başladığı yeri belli çünkü. Tamam mı? Yani bir dosyanın bulunduğu bilgiler var. Dosya nereden başlıyor, nerede bitiyor biliyorsun onu. Contiguous allocation olduğu için en büyük avantajlarından bir tanesi zaten o olur. Yani contiguous allocation'da simple only starting location and the length number of the length okay, number of blocks is required. Fast sequential, also quite fast random access. Dolayısıyla bunda problem yok. Problem, biz bir şey söylüyor burada.
Allocation yaptığımız zaman hocam file büyüme oldu mesela, ekleme oldu o zaman.
If I need to append something, if I need to make this file A 5 blocks, I need to append some data. So what do I do? There is file B in here. So appending data to files is a problem. Actually, making the file shrink is a problem too. When I shrink this file A into a 3-block file, this one will be empty and this one will be internally fragmented, externally fragmented. Okay, so external fragmentation again comes back into the picture. These are some problems with the contiguous layout. So disadvantage is external fragmentation, inflexible when appending a file. Okay, so that's why we don't use this contiguous allocation, contiguous layout much when we implement files. However, okay, this contiguous layout is still used for CD-ROMs. It is very useful for CD-ROMs. Why? We can,
ekleme olmuyor hocam yazdırdığım üzerine.
because CD-ROMs are, what is a CD-ROM? Compact disk, read-only memory, right? We don't modify it. Once we write to the CD-ROM, we don't modify it. That means that when you write your information to the disk, you write it this way, without without leaving any spaces between the files. Okay, okay. So when you put all of your files into the CD-ROM, you don't modify it anymore because you cannot, because CD-ROMs are write once only, right? Write once only. You cannot modify them. So contiguous layout, since it is very convenient for sequential access, also it is very convenient for random access too. Contiguous layout is still used for the CD-ROMs, DVDs, and that kind of write once, read many. They are called write once, read many storage units. Okay, warm storage units. For those kind of storage units, we use this kind of allocations. There is some limitation for the CD, especially for the DVDs. For DVDs, I guess the maximum size allowable is like maybe 1 gigabyte. You cannot have, for the DVD file system, okay, for the DVD file systems, you cannot have files larger than 1 gigabyte, okay? So, but DVDs can hold 4 or 5 gigabytes of data, right? So you cannot have a single 5 gigabyte file in a DVD. So DVDs divide the files into 4 or 5 files. You cannot have a very large file. Why do you think that there is a limit for this 1 gigabyte? There is a limit because when you specify that my starting location is this block and my length is this, so the length must be 2 to the power 30, right? So they only allocated 30 bits for the length field. I cannot make it larger than 30 bits. I guess that's the reason. So it's called Universal File System. I guess the name is Universal File System, UFS. Inside the UFS, you cannot have files larger than 1 gigabyte. Okay, 1 gigabyte. So people make these kind of restrictions to make their file systems more efficient. But when the storage medium gets larger and larger, these kind of restrictions becomes more and more problem. And we have to deal with those kind of problems. I mean, MS-DOS, the disk operating system, Microsoft disk operating system, couldn't handle more than 256 kilobytes of memory space for a long time, right? This was the limitation of the MS-DOS operating system, Microsoft disk operating system. And later they solved this problem, but for a while people had to live with it. Even though they have 1 megabyte of data, 1 megabyte of memory space, they couldn't address more than 256 kilobytes because the operating system couldn't support it. And again, we have the same problem for the DVDs. Even though I have 5 gigabytes of available disk space, I cannot have files larger than 1 gigabyte of data. These kind of problems, we still have them, and we will have those kind of problems in the future too. So this is contiguous layout, fragmentation, and appending file are the disadvantages, inflexible. These are the disadvantages. To solve those problems, they switch to linked file allocation. They don't do it contiguously, okay? They store their files in a linked list fashion, like this one, okay? let's say my file A has 5 blocks, 1, 2, 3, 4, 5, okay? My file B has 4 blocks, 1, 2, 3, 4. They use just linked lists, linked list allocation. So each block stores the information about the file. Also each block has a pointer to the next block. So this solves the external fragmentation problem, right? I don't need to keep my files contiguously. Also it solves the appending problem. All I need to do is just add new blocks at the end of the linked list. It solves all the problems of contiguous allocation, but it creates some other problems. What are the problems with this approach? What is the problem with this approach? All the disadvantages are solved, but all the advantages are gone now. What is the advantage of the contiguous allocation? Remember the advantages? Simple, fast sequential, quite fast random access. This is not very fast in terms of random access. If I wanted to access the 10th block, what do? I start from the beginning and I have to follow the nodes one by one. Okay? And each one is a node, each one is a different block. And these blocks are usually, remember my disk picture? This is my disk picture, okay? One block might be here, okay? Other one it might be here, then might be there, and might be there. So my linked list is something like this. This one points to here, and this one points to there, and this one points to there. Reading this data, then this data, then this, and then this is very expensive. Why? Because you need to physically move your hard disk head, reading head, okay, from one position to another position. And physical movements are very, very slow. Even though we talk about milliseconds, okay, milliseconds is a million times slower than what I can do with a memory access, right? So this is like million times slower than doing it with the memory. So if I need to move my reading head from one position to another position, if I want to follow this link, that means that the things are going to be very, very slow for me if I use this approach in terms of doing the sequential access and the random access. You might say that I have the same problem with this approach too, because you need the blocks one by one, right? I don't have that sequential access problem in this. I have the problem, but it is not that serious. Why do you think it is not that serious? With the contiguous allocation, I don't have this problem. This problem is not that important. Moving from one position to another position. Contiguous allocation doesn't have this problem. Why? Because in the contiguous allocation, all of my data is contiguously kept on the same track. So if I am reading it this way, okay, I don't need to move my disk. I don't need to move my disk head, reading head, from one position to another position. All I need to do is just rotate the disk. Okay, rotate the disk this way. The disk is rotating already 5,400 rounds per minute, or sometimes 10,000 times rounds per minute. It's very, very fast. So rotating the disk is not that slow compared to the disk head movement. So contiguous allocation is very fast in terms of accessing the sequential file data or the random access file data, because I can read the whole track in a very, very short amount of time compared to the disk head movement. So sequential and fast random access is the advantage of this contiguous layout. Okay, but it has the disadvantage of external fragmentation and inflexibilities with the file appending. And the link, when I use the linked file allocation, okay, advantage is space efficient and flexible in appending. So the disadvantage becomes the poor per access key, sequential and random. And we have to solve this problem. How do you solve this problem? How do you solve this problem? Especially the random access problem. I mean, how do you access the fifth one? You start from the 0, then this one, then this one, then this one, this one. I don't want to do this, okay? I don't want to read all the blocks from the disk because each read requires me to move my diskette from one position to another position, which is expensive. I don't want to do this, but I want to keep this structure. Yes.
Hocam aynı track üzerinde ama birbirine çok yakın olmadan tutsak.
Ama o zaman şu probleme dönüyorsun sen, şuna dönüyorsun. Yani böyle koyalım diyorsun. Böyle yaparsan yapabilirsin bunu. Aynı sürekli üzerinde. İşte aradan bir tane dosya sildin, yenisini koydun, append ettin falan filan bozulacak onlar.
Farklı segmentlerden eşleri mi tutsam? Eşleri dolu tutsak adresleri.
Hangi adresleri?
Blokları birbirine bağladık ya. Birbirine bağlamak yerine tablodan direkt seçip değişebiliriz aslında.
Bu blok adreslerini burada birbirine bağlamak yerine bu blok adreslerini bir tabloda tutsak diyorsun. Anladınız mı? Yani böyle linked list olsun yine ama bunun arasındaki bağı buraya koymayalım da bir tablo tutalım, bu daha hafıza dursun tabloda. So if I keep all this information in memory, okay, table in memory. If I keep this information in memory, that means that I don't have to skip from one block to another block to be able to access the fifth block. All I do is keep this file in my memory, okay? So let's say file A starts here. So when I come to this position, this is a memory table, okay? And accessing the memory is very, very fast. It says that physical block 4 is where the file A starts. Then I follow this 7. 7 is 2, 2 is 10, and 10 is 12. 12 is minus 1. So my file A ends here. So without reading any disk, I can do my random access without doing any disk reads. Let's say I wanted to access the third block. All I do is this one, and this one. So this is my third block. I go there and now I have to go to disk and read it. So in order to make this random access, all I need is a single disk access. Okay, I don't have to do this movement many times. So this solves the random access problem, but I still have the sequential access problem, because if I want to read the whole file from beginning to the end, I have to follow each block, and I have to move my disk head from one block to the other block, which will take time, and I cannot escape from it because I started my file system this way. Okay, so this is called, again, this is a linked list approach, but instead of keeping my links inside my blocks, I keep my links inside my memory. But this has some other problem other than the sequential access problem. What is the problem with this approach? The primary disadvantage of this approach is, see, the operating system people are never happy. They always have some problems. And at the end, when they say that this is my operating system, when they say that, they will not be happy either. They will say, okay, this is my operating system, but this has such and such and such problems. You will never solve problems together. Okay, so what is the problem with this approach? The problem with this one is memory. Yeah, you need memory to keep. You need memory to keep this table, right? And this table might be very large. Let's say I have one terabyte of this space and 1 gigabyte of memory. Okay. Let's say my blocks are 1 kilobytes each. So what would be the table size for this kind of system? 1 terabyte is what? 1 terabyte is 2 to the power 40? 50 or 40? Yes. This is 2 to the power 40 is my this size, okay? And I need to have a single table entry for each kilobyte of data. So I need to have 2 to the power 30 elements inside my table, right? Because each block is 1 kilobyte, and 1 kilobyte is 2 to the 10. So I need this many elements in my table. How much is this? This is 1 gigabyte, right? So I need to keep a table of this almost my it is the same as my main memory size. Okay, if I want to keep this whole thing inside my memory, then I will have some problems. So what are the optimizations? Don't keep all of it in your memory. Keep only some small part of it, the ones that you are using, and etc. That kind of solutions might exist. But this is the approach that Windows and MS-DOS use for a long time, and that approach is called file allocation table (FAT). Okay, remember this file system FAT16 and FAT32. So these two systems are using this approach, and they need very large memory space to keep this data. They have no external fragmentation problem. They have no random access problem, as we described before, but they have this large memory requirement for the table problem. Okay, so let's look at this file allocation table. Advantage of linked list, no access. The disadvantages still need to traverse. Still, I need to move my head from one position to another position if I am doing the sequential access, and I need lots of memory for this table, file allocation table. Again, for the memory, if I have 2 gigabytes of this space, 1 kilobytes block, that means that I have 200 megabytes of memory requirement to keep this table, which is very, very large. Okay, so file allocation table is one solution that solves some problems but causes other problems. UNIX has some solution for this problem. UNIX says that okay, this is a very good approach. Let's use this approach, but I don't want to keep all of this table, FAT table, okay, file allocation table inside my memory. I want to keep the file information. I want to keep this information only for the open files. Okay, let's say if I have 2 files open at the same time, keep that information in memory only for the open files. Since I cannot have all of the files open at the same time on my disk, that means that I will not have that much memory need. That's the idea for inode, okay, index node. Okay, brings all pointers together into an index block like this one. Okay, these are index information, right? It does the same thing. Okay, brings all pointers together into the index block. There is an index block. There are many index blocks actually. That's why it's called inode index node. Okay, just keep all attributes and analysis of each block belonging to the file in the structure, and keep in memory only when the file is open. So I keep this information in my memory when the file is open. Otherwise, I don't keep it in memory. Okay, so it's very space efficient, like the file allocation table FAT system, and access speed is the same stuff, but I don't have this large memory requirement for this approach. UNIX, ext3, ext4, UNIX or UNIX file system and the NTFS file system uses this approach of inodes. So the Windows system doesn't use file allocation tables anymore, and UNIX, the newer version of Linux, ext3, ext4, uses this kind of approach. It's called inode, similar to this one, but it is used only for the open files. Okay, let me show you some example here. Okay, so an example inode is this. What is an inode? Inode is, okay, it's a node that keeps just the index information, okay, along with the attributes. I have the file attributes here, the file name, the path, the read-write permissions, access times, and etc. Okay, and after that, I have the address of disk block 0. So this is just the index. So address of disk block 1, disk block 2, disk block 3. It goes like that. Okay. So I have the address of disk block 7, and then this is my whole block. Okay, this is my whole block. If my file is at most 7 kilobytes, then this is good enough. But if my file is larger than 7 kilobytes, the last one is a link to another inode, okay, which contains the addresses of the other blocks. Okay, so this is the structure of an inode. This is the structure of an inode. In fact, let me show you the solution for the 39, right? Let me show you the solution for the, I guess, which one I forgot. If I can find it. Yes, okay. UNIX v7, which was very, very popular. So the inode attributes, okay. So 1, 2, 3, 4, 5, 7, 8, 9, 10. For 10 inodes, I have, for 10 kilobytes, I have enough information. For the 11th one, I have another table like this one. Now I can make it like 20 kilobytes of data. But if this is not enough, then I have another type of table. This table now, each one points to not a block but another table. So this would be my 2-level inode. If this is not enough, then I have 3-level. So it is getting more and more complicated if you have a larger file. If you have smaller file, this structure is enough for you. Okay. So it is both fast because it is very small for small files. If the files get larger, then it gets larger and more complicated. So this is the structure for UNIX v7, and its similar structure is used by the modern operating systems. Okay, so this is the inode structure, which is not very different from this file allocation table structure, but it is only for the open files. When you open a file, again, the same question. Why do you open files? Because we need this kind of information. We need to keep this kind of information inside my memory. Okay, my starting address, my blocks, where are they, and my links. All that information needs to be kept inside the memory. And I cannot have millions of files open at the same time, because if you keep millions of files open at the same time, you need to keep all that information in your memory, which is very, very long. That's why you open your files, you use it, and you close it, so that you don't waste your system resources. Okay, any questions? Okay, so this was again what we are doing here. We are implementing our files. Since directories are special kind of files, we are going to look at how the directories are implemented as the next step. Okay. The directory entry provides the information needed to find the disk blocks. Okay. The directories are files, and they are stored as files. But inside the directories, there are information to find how to find those disk blocks and etc. And it is mostly system dependent. Okay. This information could be the disk address of the entire file, or the block address, or the number of the inode. Okay. So it is dependent on the system. But the thing is that in all cases, the main function of the directories is to map the ASCII name of the file onto the information needed to locate the data. Okay, what is the ASCII name of the file? My ASCII name of the file is under the root, there is user, there is ABC, there is test. Okay, so take this ASCII string and convert this into either disk address or to block number or the inode address. So get this string and give me a disk address or the block number or the inode. This is the function of the directory. Okay, so if we implement the directories in a very primitive way, this is what we do. Implementing directories, simple directory. Okay, when you open a directory, you have the file names and their attributes. Fixed file names, okay, fixed attribute set. This is called fixed size entries. So like a table, okay, you can extend the table, but each table entry is fixed. Okay, each table entry is fixed. Sometimes you keep all the information inside this table, or sometimes you might have pointer to point to some other space that contains all the attributes. This is called a simple directory structure example. Okay, this is a simple design. Everything is fixed. Okay, and you can keep all of your data in these fixed data systems. Okay, so with the fixed system, with the fixed directory system, everything is simple. This is the advantage. The disadvantage is, since everything is fixed, I cannot have varying number of file name characters. So all I have to do is, let's say these are my names. I cannot have more than let's say 8 bytes for the file name and 3 bytes for the extension. This was the case for the MS-DOS systems. Your file names has to be at most 8 characters long. Your extensions can be at most 3 characters long. And you cannot have special characters or the Unicode characters inside your file names. For example, you cannot have this character or this character or this character inside your file names, because only ASCII characters can be used as the file name. So these are some limitations for these kind of directory structures. So instead of doing this, people started using this kind of a structure. Okay. So again, this is fixed. Let's say this is 100 bytes of data. Each file has to have at most 100 bytes of data, and 11 of which is the file name. You cannot have less, you cannot have more. You have to do it 100 bytes, which is inflexible. So instead of doing that, people started doing this. Okay, this is my file 1, this is file 1, file 2, and file 3. Instead of fixed length entries, I have the file 1 entry, file 1 attributes, and my file name. This file name can be as long as you want. Okay, it terminates with a terminating character, a null character. Okay, and I start my file 2, and I start with my file 3. So in this way, you can have very long file names, and you can have Unicode file names too. This is one solution. But the problem with the solution is that the nice thing about this one is, I know that each entry is 100 bytes. So if I wanted to go to the third file, I just do 3 times 100, right? 300. Random access is very fast. I just make a multiplication. For this one, to go to the third file, you need to run through your first file, and the second file. Now I can go to my third file. So I need to do sequential access to be able to go to the third file, which is bad. I don't want to do this. So they said that, okay, I don't want to give up my any length file name feature, but I want to do this in a very, very fast way. So they implemented this. So what is this? What is the solution? Can you see it? Each file entry is fixed length again. Okay, this is fixed. This is one entry for file. This is fixed again. This is the second file, third file, fourth file. Each one takes again 100 bytes, but inside the files, file attributes, there is a pointer to the file name. Okay, and I keep my file names in a heap, in a different place. So this heap can be large or small. It depends on the file names, but I can access my third file immediately by multiplying this number with number 3. Okay, so it is as fast as the previous approach, but I can still keep my any length file names within my directories. So these are the types of solutions that we are now using for the modern operating system like Unix or Windows. For my system, Unix or Windows, my file names could be any character long. I can use my Turkish characters with no problem inside my files, okay, because they are using these kind of structures. Is there anything that I missed here? We talked about fixed design, and the second one is, okay, the fragmentation problem. We talked about this. Okay, I guess I didn't. I think I talked about all of these. Okay, so this is the solution for using different varying levels of varying number of characters inside my files and keeping the file structure fixed, attribute fixed. There are still many problems to be solved with the directories. For example, if you have thousands of files inside your directory, accessing your files will be difficult again. If you have more than 1,000, 10,000 for each character, right? So how do I do this? I mean, to find something in a 1,000 long list will take some time because you need to do the linear search. I don't want to do the linear search. What would be the solution? So next time we will look at the solution on Wednesday. Tomorrow I will not be here. Mohammed will do the problem session. On Wednesday we will continue from this point. Okay, any questions? Okay, see you on Wednesday then.